Why are complex oscilloscope waveforms so hard to understand? Imagine trying to read a map with hundreds of roads crisscrossing in every direction. That's what complex waveforms on an oscilloscope can feel like. When you look at a waveform that isn't just a simple sine wave, it can seem confusing at first. That's because these waveforms are made up of many different signals combined into one. Think of a musical chord with many notes playing together. Each note is like a different frequency in the waveform. The oscilloscope shows you the shape of the combined signal, but it doesn't tell you what each part is right away. To understand these waveforms, you need to know about the Fourier series. This is a way to break down a complex waveform into simple sine and cosine waves. It's like taking a complicated song and isolating each instrument. Once you see the individual parts, it becomes easier to understand what's happening. But this process isn't automatic. You need to use tools like the Fourier transform or filters to analyze the signals. Another reason they're hard to understand is signal integrity. When you connect a probe to measure a waveform, the probe and the settings on the oscilloscope can distort the signal. If the probe isn't high quality or the settings aren't right, the waveform you see might not be exactly what's happening in the circuit. This can make interpretation tricky. Plus, complex waveforms often have many frequency components. Some are fundamental frequencies, which are the main signals, and others are harmonics or noise. These can change rapidly or overlap, making it hard to see what's important. Adjusting the oscilloscope's time base, voltage scale, and trigger settings takes practice. If you don't set these correctly, the waveform can look distorted or unstable. In real-world electrical systems, these waveforms are common. Power systems often have harmonic distortion, which shows up as complex shapes on the scope. If you don't understand what these shapes mean, you might miss problems like power quality issues or faults. That's why mastering how to analyze these waveforms is so important for electrical engineers. Getting good at interpreting complex waveforms also means gaining experience. The more you practice adjusting the scope and analyzing signals, the better you'll become at recognizing what's normal and what's a sign of trouble. Using techniques like filtering or Fourier analysis helps to isolate specific parts of the waveform, making it easier to understand. So, the main reasons complex oscilloscope waveforms are hard to understand are because they contain many different signals, requiring precise settings, and need some analysis tools to break them down. With practice and the right techniques, you can learn to read these signals clearly and use them to troubleshoot or improve electrical systems.